Can you see my slides?
Yes.
Excellent. So hello, my name is Sebastian Mosbach. I'm from the Chemical Engineering Department at the University of Cambridge. And today I would like to talk about chemical ontologies in the world avatar. So if you hear the word avatar for the first time, it probably sounds a bit ambitious. So I guess I should explain or try to explain what it is about, because there is a serious point. So when you build ontologies, so you start assembling concepts and relationships, one thing you realize very quickly is that it's an endless task. So everything in the world is connected. So if you try to develop a domain, an ontology for a particular domain, you have to make an arbitrary decision to stop somewhere. And so the word avatar is really just acknowledging the fact that everything is connected. So rather than trying to build a model for a particular domain, we take the view that everything is connected in a single graph. So we shouldn't be designing systems for particular domains. You might as well do it generically. And this is, I guess, the key point. I mean, we're not saying we have developed a model for the entire world, or that we can, because that's obviously impossible. It's simply, the name just reflects the mindset that everything is connected. And I guess one other aspect to point out is probably, even once you've built ontologies and represented your data in this way, the data that you represent is not static. So data changes all the time. And so we represent this through agents. They're basically pieces of software, if you like, that act on this knowledge graph. So they add new things, they delete things, they change things, they update things, they process, create new things, and so on. So the dynamicness of the evolving knowledge graph is captured by these agents. And so in this spirit, I suppose, I mean, over the years, we've been working on this for more than 10 years. So we've had a multitude of applications. And so naturally, they're all cross-domain and across the scales. So literally from, I mean, the entire link scale, if you like. So we have at country level, for example, we've looked at policies, the impact of different policies on implementing heat pumps and how this impacts social inequality. At regional level, we looked at how infrastructure, for example, water, telecoms, power, and so on, how these infrastructures can be set up in a resilient fashion when in response to disasters, let's say. We've looked at how to supply heat to multiple cities in an optimal fashion. We've looked at how to plan cities in an energy efficient way. We've looked at individual buildings and the things that buildings contain, for example, I mean, more relevant to this audience, let's say a chemical lab in a building, and how this can be run sustainably and in an automated fashion, and all the way down, of course, to the molecular scale, where we look at designing new materials, designing new molecules, and doing even quantum calculations for molecules. And I guess, I mean, the point here is that these are not separate, unrelated use cases. This is all implemented in one and the same infrastructure. It uses all the same technologies. So it's a single kind of system that is all integrated in. Now, in the chemistry domain, we've been working on this since 2010, essentially, when we first started with Peter Murray Rust's chemical markup language. And since then, we've dived into a number of different subproblems, I guess. So, and this spreads the whole area between computation and experiment. So naturally, ontologies for species and reactions are central to chemical themes. as I mentioned, we've developed an ontology for quantum calculations for individual molecules. And I mean, historically, we've done quite a bit of work in the gas phase. So we've developed an ontology for the reaction kinetics in the gas phase. And also an ontology for potential energy surface scans. So this basically connects reactions in computational chemistry. And more recently, we've looked into flow chemistry problems, mainly synthesis in the lab. So we've looked at specifically lab automation. So we've developed an ontology for representing your typical lab kit that you would have when you synthesize something. And this also includes a design of experiment, algorithms that allow you to design the next experiment, and a whole bunch of lab kit. So this naturally relates to ontology for devices in general. And for example, when you start looking at fume cupboards and so on, this then naturally connects to what's in your building and so on. And most recently, I guess we've looked at reticular chemistry. So specifically, we've looked at metal organic polyhedra and covalent organic frameworks. And it's not just about representing those as molecules, but also how to make them. So you know, at the end of the day, we want to discover new materials, but it's not just about the material itself. You also want to know how to make it in the lab. So this is a selection of things we've looked at in the chemistry ontology space. Given that we are fairly short on time, I will skip a few of these. So yeah, I mean, all of these are open source. These are all selections of ontologies in different spaces, I suppose. Let me just pick out one, which is the most recent one on the reticular chemistry. So this is even more specific. So this is metal organic polyhedra, where not only do we represent the molecules themselves, really as species, so with atoms and how they connect and so on, and the molecule as a whole, together with the individual chemical building units, but there's also a level of abstraction in it. So there are many such polyhedra, but they come in different shapes, and many of them have these shapes in common. So it's really just in a way topological or a combinatorial way how the elements connect together. So we have introduced abstractions, an assembly model that tells you something about the structure of the molecule, and together with the units, we call them generic building units, with which you can make them. And so this allows for a lot of generalization and for material discovery, which was our main aim in this project. Yes, and I guess that is probably all I have time for. So there's too much material that could possibly be shared, but obviously all of our work is open source essentially on GitHub. All of our publications are as preprints available freely on the internet. And obviously we are very happy to work together with anyone in the space of chemical ontologies. So yeah, thank you very much.
Thank you very much, Sebastian. So that was quite interesting.